Welcome to Lecture 7.3 on Linear Programming Applications. What we're going to do is we're going to use the skills we learned in our last section about how to find the maximum or minimum of a problem, but we're going to do it now with word problems. So we're going to have to first translate the problem into an objective function, which is what we're trying to maximize or minimize, and then identify all the constraints and make those into inequalities. So we're going to do a number of examples today and using the same kind of method each time as we go through. So let's look at our first example. This is a business example. An office manager needs to purchase new filing cabinets. He knows that ACE cabinets cost $40 each, require 6 square feet of floor space, and hold 8 cubic feet of files. On the other hand, each Excello cabinet costs $80, twice the cost, requires 8 square feet of floor space, and holds 12 cubic feet. His budget permits him to spend no more than $560, while the office has room for no more than 72 square feet of cabinets. The manager desires the greatest storage capacity within the limitations imposed by funds and space. How many of each cabinet should he buy? Okay, as I've talked to you before about word problems, really what you want to do as soon as possible is identify what the question is. And it's almost always the very last sentence in a problem, okay? And this is really true on any kind of math problem that we're doing, word problem, is what are we looking for? This is going to be our variable. So we're looking for how many of each type of cabinet. Well, that doesn't really help us because we need to know how many cabinets we're thinking about. And so remember that when we were reading through this, we had two types of cabinets. We had ACE cabinets. Let me put my pointer going. We had ACE cabinets, and then we also had Excello cabinets. So I'm going to use the variables A for the number of ACE cabinets and the variable E for the number of Excello cabinets. I recommend that you do this, that you use variables that are connected to the problem. This will help you stay focused on the problem and also not interpret the results the wrong way at the end. If you just used X and Y, X for ACE and Y for Excello, it'd be very easy at the end to go, oh, X is Excello, but it's not, okay? So use letters that are related to the problem. This is the first thing we're going to do every time is identify what we're looking for and create variables or letters that represent the things that we're looking for. The next thing we're going to do in these linear programming problems is identify the objective function. What are we optimizing? What are we looking to make the most of, the least of, to find the maximum, or to find the minimum, okay? So when we look at the problem, the manager desires the greatest storage capacity, okay? So we need to write an equation using the variables from number 1 that identifies how much storage we're going to get from each of the cabinets, or in total really, okay? So remember that ACE cabinets require 6 square feet of floor space. Now that's not how much they're storing. This is telling us how big the cabinet is when we're looking at the room. And they hold 8 cubic feet of files, okay? So 8 times the number of cabinets, ACE cabinets, which is A, and then Excello cabinets hold 12 cubic feet, so we get 12 times the number of Excello cabinets, okay? Next, we're going to identify the constraints, okay? Constraints are limitations that we have, okay? And this is very common. We can see that his budget permits him to spend no more than $560. Cost is always a constraint everywhere. And the room has no more than 72 square feet of cabinets, okay? So we have two constraints, which is about the amount of money we can spend, and we know how much each costs. And we have a constraint about how much floor space we have, and we know how much space each takes up. So we can write these, and it even tells you here in this last sentence that our constraint or our limitation is money and space. So we have $560 maximum. Remember that no more than is actually a less than or equal to. So our budget has to be less than or equal to $560, and we have no more than 72 square feet for the cabinet. So again, that's a less than or equal to. Be very careful when you're translating these. It's very easy to move through quickly and see no more, see the word more, and think that it should be greater than or equal to, but it's exactly the intuitive opposite or counterintuitive. So ACE costs $40 each, so 40A. Excello costs $80 each, so 80E. So 40A plus 80E has to be less than or equal to $560. Our space, each ACE cabinet takes up 6 square feet, so 6A. Each Excello cabinet takes 8 square feet, so 8E has to be less than or equal to 72 square feet. Now there is another limitation here that we haven't addressed, and it's important to think about. You know, can we have negative number of cabinets? No. So both the number of ACE cabinets has to be greater than or equal to 0, and the number of Excello cabinets has to be greater than or equal to 0. And this is pretty standard, right? Because we're looking for something. Negatives usually do not apply into practical world problems when we're trying to figure out what the variable is or the answer to our question. Okay, so now we see we're in quadrant A. We have two different inequalities that we're going to graph as lines, and then find the corners. Remember that? Graph these two lines, really 4, because we have the x and y axis. Then look for the corner points or the intersections and find the feasible region. Once we found the feasible region, we're going to look for all the corners and plug all the corner points into this A and E objective function to find the, are we looking for the maximum or the minimum? Did we know that? Let's go back and see what he's looking for. What are we looking for? We're optimizing storage capacity. He desires the greatest storage capacity. Okay. So here's all our equations. Again, we're going to do it exactly like we did before. Sometimes a table can help. I'm not sure, but you know, if you built this first, it might help. Then you can see how to do each one. Of course, they used x and y, which I don't really like, as I mentioned. All right, when we graph this, we get two different lines. It's very confusing here, so you really have to figure out where the feasible region is by, you know, doing what we did before. We would have 4 quadrants, 1, 2, 3, 4, 1, 2, 3, and 4 to figure out which one we're shading. Okay. So you need to be very careful in that you shade the right quadrant because we're going to have different corners. So we have 0, 0, 0, 7, 8, 3. And this point you probably had to find by looking for the intersection between these two lines, as we talked about using our TI-84 calculator. And then, of course, this last one. Okay, we take those 4 quadrants, those 4 corners, we plug them into the objective function. We're looking for storage space. We plug in those values, and we get 0, 84, 100, and 96. This is the amount of storage. Remember, the objective function was how much storage we would have. We're trying to maximize that, and so we get 8, 3. Okay? It's important that you then interpret this, and this is why I use A and E instead of X and Y, because it helps me. Here, A is X and E is Y, so plugging in the parenthesis 8, 3 into this problem will get you the wrong answer. This is what you need to say, that the manager should buy 8 ACE cabinets and 3 Excello cabinets, because that's what the question asked. How many of each type of cabinet should they buy to maximize storage with the limitations of cost and floor space? All right, so let's try another problem and see if we can do this one as well. Certain laboratory animals must have at least 30 grams of protein and at least 20 grams of fat per feeding, period. These nutrients come from food A, which costs 18 cents per unit and supplies 2 grams of protein and 4 of fat, and food B, with 6 grams of protein and 2 of fat, costing 12 cents per unit. Food B is bought under a long-term contract requiring that at least 2 units of B be used per serving. How much of each food must be bought to produce the minimum cost per serving? Okay, so let's go back. We're looking for how much, what are we looking for? How much of each food? And notice we have A food and B food. Okay, so those are our variables, A and B. Then we need to identify the objective function. What are we optimizing? What do we want to maximize or minimize? We want to minimize the cost per serving. Okay, so our cost per serving. Well, how much does each serving cost? Well, A costs 18 cents and B costs 12 cents. So our objective function is 0.18A plus 0.12B. Okay, cost per unit times the number of units of A. Cost per unit times the number of units of B. Okay, again, what are we looking for? Variables. And then what are we maximizing or minimizing is our objective function. Finally, what are our constraints? These will be our inequalities. Certain laboratories must have at least 30 grams of protein, so greater than or equal to. Again, see how this works and is counterintuitive? At least 30 grams of protein is greater than or equal to 30 grams. And it's very easy, again, to get these wrong intuitively. Okay, well, A has 2 grams of protein, okay, and 4 grams. Let's do the protein first. So we need at least 30 grams of protein. So A has 2 grams of protein, so 2A. B has 6 grams of protein, 6B has to be greater than or equal to 30. And then with we need at least 20 grams of fat. So we need A has 4 grams of fat, so 4A, and B has 2 grams of fat, 2B has to be greater than or equal to 20. Protein is greater than or equal to 30, fat is greater than or equal to 20. There's our protein, there's our fat. Okay, now we need to make sure there are any other constraints. Of course, we can't have 0 of A or B, or excuse me, we can't have 0. My bad. We can't have negative amounts of food. What is that when you throw up? I'm not really sure. Okay, but let's read something here. It tells us here that food B is bought under a long-term contract, so we've requiring that at least 2 units of B be used per serving. So instead of A and B has to be greater than or equal to 0, B has to be greater than or equal to 2, because we're in a contract that says every time we create food, we have to give at least 2 units of food for B. So be mindful of those kind of things. It's hard when you have a paragraph here to make sure you don't miss each sentence. So once you've got the objective function, when you're doing the constraints, read through and say, is that a constraint? And you can usually see it because at most or at least are words that tell you that it is a inequality, and remember that it is counterintuitive. At least means greater than or equal to. At most means less than or equal to. Okay. We now have our objective function. We have our constraints. We can graph our lines and then find the feasibility area. Okay. Again, you can build a table if this helps you a little bit better. Sometimes it really does. If you just think about it, I kept going back to the paragraph to find these things, but you could, and here we have the values that we're constrained to. It has to be at least 30. So then it's just 2A plus 6B, and again they use X and Y for A and B, which I don't like. Anyway, but I can see where it could be confusing. This is another interesting graph. It's an unbounded graph, so there is no maximum because it keeps going up. But it's another graph where we have lots of different areas here, right? So, sometimes you can intuit it because we know that, for example, we have to use at least 2 of B. So that was the Y equals B. It's everything above this line. So, but even there, we know we have 1, 2, 3, 4 areas that we could be potentially. Okay, so you're going to have to make sure that you find the feasible region. Notice that we have 1, 2, 3 corners on this feasible region. There are no corners at the top because it just keeps going up. Okay, so we have 0, 10, 9, 2, and 3, 4. You'd be for 2 of these, you'd have to use your calculator in the intersection function, looking for the intersection between 2 lines. For example, where my pointer is now is the intersection between 4x plus 2y equals 20 and 2x plus 6y equals 30. So if you made sure you're on both of these lines, your calculator would then tell you the coordinates 3, 4. Here we have y equals 2, so we can just plug that into the y value in this equation and solve for x. It's pretty simple. Or you could use your calculator again. Excuse me, we plug in the corner points into our objective function, which was about food, it's about cost, to minimize cost. And we see that 0, 10 is our first corner, 3, 4, and 9, 2. We see that our lowest value is 1.02, and this is our minimum value. Okay, now make sure you answer the question, how many units of each food? 3 units of food A and 4 units of food B will produce a minimum cost of $1.02 per serving. Okay, so it's not only important that you figure out how to find the minimum value, but you know what these values mean. What does 3 mean? What does 4 mean? What does 1.02 mean? Okay, so remember we were talking about cost, so the 1.02 is the minimum cost. 3 was the amount of group food A, and 4, or Y, was the amount of food B. It's very important that you can interpret your results. Let's look at another problem. One measure of the risk involved in investing in a stock or mutual fund is called the standard deviation. The standard deviation measures the volatility of investment returns relative to a historical average. If the return of an investment tool fluctuates a great deal from the historical average return, then there will be a higher standard deviation value for the stock. If an investment tool value stays near the historical average, then it will have a small standard deviation value. Thus, a higher standard deviation for an investment tool can be one measure of higher risk. Higher deviation, higher risk. Higher deviation, higher risk. Investors often wish to obtain the highest profit while minimizing the risk, right? So if we're trying to minimize risk, we're looking for a lower standard deviation. All right, so let's look at our problem now, given that idea about standard deviation. Carolyn wants to invest up to $5,000 in stocks. The share price for the Costco Whole Corporation is $108, and it has a standard deviation value of 15.9. The share price for CVS, Caremark Corporation, is $59, and the standard deviation value is 19.5. Based on the average 10-year of returns, Costco would produce in a year a profit of $15 per share, and CVS would produce a profit of $10 per share. Carolyn would like to obtain at least $800 in profit. How many shares of each stock should she purchase to minimize the risk as measured by the standard deviation, and what is the minimum value of the risk? Okay, so let's look at what we need to do. Okay, the first thing is, what is our question? How many shares of each stock? Well, we have CVS stock and we have Costco stock. Okay, here we're going to make C equal Costco stock and V equal CVS stock. What is our objective function? What are we trying to maximize or minimize? We're trying to minimize the risk and the risk per standard deviation. Okay, now remember that the standard deviation of Costco is 15.9. The standard deviation of CVS is 19.5. So we can then plug those values in. 15.9 times the number of shares of Costco, 19.5 times the number of shares of CVS. Then we have to identify the constraints, right? What are our constraints? How much money does she have to spend? Usually that's always a constraint. Carolyn wants to invest up to $5,000 in stocks. So that's our first one. What else does she have? She wants to minimize the risk. Okay, I'm sorry, I went blank there. And she wants to have at least $800 in profit. She invests up to $5,000, so this is less than or equal to $5,000. And she wants at least $800 in profit, so this is greater than or equal to $800. Okay, again, pay close attention how these are counterintuitive. So the share price, the cost, or our investment is 108C. The cost for each share of Costco plus the cost for each share of CVS has to be less than or equal to 5,000. That's how many shares we can buy. The profit, how much we had a projected profit of $15 per share for Costco and $10 per share for CVS. Again, we cannot buy negative shares, so both of the number of shares of Costco and the number of shares of CVS have to be greater than or equal to 0. Again, we're going to go through the same action again. We're going to graph these lines. We're going to turn them into equal signs, graph the lines. We're in the first quadrant. We're going to find the feasibility region and then find the corner points. Again, a table can help. It really can help if you're trying to pull out this information, and then it's almost always, you know, the value here times the variable plus the value here times the variable is less than or equal to or greater than or equal to the constraint. Okay. All right. So here are our lines graphed. Again, we have possible 4 different regions to figure out. Using your calculator, it's a good idea to kind of see, to actually use the inequalities when you're graphing them. Your calculator will actually graph an inequality and shade that area. And do a Google search for that, like how do I graph an inequality on a TI-84, and it's a pretty good tutorial. Okay, I have 3 points, 0.80, 0.84.7, 14.4, and 58.4. When I plug these in, I get 1651, 1560, and 1367. What am I trying to do? What was our objective function? We were trying to minimize risk. So we're looking for the lowest value, okay? The lowest value, okay? We were minimizing risk, okay? So our goal here is to buy 14 shares of Costco and 58 shares of CVS, okay? That's the end of our lecture for today. We did 3 different examples. They're all done in the same way. This is a challenging part. I get it, to kind of graph it and find the feasible area, and then also to find the corner points. All right. So if you need anything, reach out to myself or to the tutors that are available to you, and we'll see you in the next lecture.